For our last scalability from the mean value theorem that we're going to discuss in this section, we're going to find the derivative of the inverse function based on the derivative of the original function. And to this end, let me remind you of something that you have seen before. So derivative of the inverse a picture that you have seen before. So let's draw a graph of a function f of x. And we also want to draw a graph, the graph of an inverse. And the inverse is supposed to be symmetric with respect to the graph of f about the line y equal to x. So if this is, if this is going to be y equal to x, and maybe this is f of x, or y equal to f of x, then graph of the inverse is going to be a reflection of this one. Use a different color for that. So it's, roughly speaking, a graph of this sort. So this would be x equal to f inverse of y, but then we, of course, interchange variables, so then this would also be y equal to f inverse of x. And then we know that if I look at a point, let's say up here on the graph of the inverse, it is symmetric to another point down here on the graph of the original function. And if this point has coordinates, first point has coordinates x0, y0, then the second point will have coordinates y0, x0. Right? And then the slope of the tangent line to the red graph is going to be a reciprocal of a slope to the first graph, because basically in a red graph y plays the role of x plays the role of y, so dy dx becomes dx dy, so the derivative should be reciprocal. And from that we can obtain the following formula, that if I take so let me write things this way. So if f is a reciprocal, f inverse is the inverse function of f, then we know that f inverse of f of x should be equal to x, right? F and f inverse will cancel one another. Likewise, f of f inverse of y, right? Because f inverse when we're drawing pictures like this, then we are interchanging x and y, and certain features of the inverse relationship between two functions is becoming less transparent. But what is important about an inverse is that the inverse cancels the effect that f had an original function. So if I use f inverse of y, I go from y axis into x axis and I apply f to this x that I got, and I recover my original y back. In the same way, if I take an x and I compute f of x, I go from x axis to y axis, then f inverse of y will give me x back. So we have these two cancellation properties. And from those properties, we can actually see, for instance, if I use a chain rule and take a derivative of the second property, then what I'm going to get is that f inverse or f prime of f inverse of y, right, times f inverse of f inverse prime of y. This has to be the same as derivative of y with respect to itself, and that is equal to 1, right? So this is by the chain rule, and then I can solve this equation for the function that I'm trying to find, so the derivative that I'm trying to find. Essentially, I'm doing implicit differentiation. And this will give me f inverse of prime of y. This should be equal to 1 over f prime of f inverse of y. Right, so if I'm trying to compute the derivative of f inverse at some point, then the derivative is just 1 over f prime of 1 over f prime evaluated at the point which is f inverse of y, right? And f inverse of y is x that was related to y there via this direct inverse function relationship. So we have 1 over f prime of a corresponding x. So basically the formula that I recovered here from implicit differentiation or the graph both indicate, so actually let me write the same thing that follows from the graph. So f inverse prime of x0, we said, is a reciprocal of y0, sorry, is a reciprocal of a derivative of f of x, now evaluated at x0. So 1 over f prime of x0, and then again, the expression that I got from a picture, and the expression, this one, and from the picture and analytically, they're exactly the same, right? Because let me amend this a little bit. So what is x0? x0 is f inverse of y0. Right, so the formula indeed is the same. All right, and so now what I want to do is I want to actually prove that this formula is true. right? Not by using the implicit differentiation, nor by picture, but I want to actually prove that this result is going to hold. And this gives us the following theorem. So let's suppose that that f is a one-to-one continuous function on an interval AB. And suppose also that f is differentiable at some point x0 inside AB. So if f is differentiable at some x0 in AB, then f inverse is differentiable at y0 that belongs to f of a, f of b, where so where y0 is f of x0. And further, the formula that we already established holds. F inverse prime of y0 is 1 over f prime of f inverse of y0. Okay, so this is what we want to prove. So let's do this. One thing that I forgot to mention, of course, the expression 1 over f prime of f inverse of y0 should hold. So we need to amend the statement here by actually explicitly saying the derivative at x0 is of f at x0 should not be equal to 0. So let's do that. And f prime of x0 is not equal to 0. So then differentiability holds for f inverse, etc. Okay, sorry. Okay, so now let's do the proof. If if x0 belongs to AB, then y0 equal to f of x0 belongs to f of a f of b. Without loss of generality, I'm assuming that if the function f is 1 to 1, then it's either monotone increasing or monotone decreasing on AB. So without loss of generality, I can assume that the function is monotone increasing, so then y0 should be between f of a and f of b. And notice that x0 cannot be exactly equal to f of a or f of b, right, because the function is 1 to 1. So I'm going to put without loss of generality here in this implication. And okay, so we have this. Then what do we know? F prime of x0, which is not equal to 0, is by definition of a derivative is a limit x converges to x0 of f of x minus f of x0 divided by x minus x0. And what this means is then the following. If a derivative is not equal to 0, and because the function is 1 to 1, so f of x minus f of x0 is never equal to 0, right? Because f is 1 to 1, f of x equal to f of x0 only if x is equal to x0. Then the function x minus x0 over f of x minus f of x0 is defined for all x not equal to x0, and so hence by properties of limits what I have is that the limit x goes to x0 of x minus x0 over f of x minus f of x0, this should be 1 over f prime of x0. Right, so in this case, I can just take a reciprocal of my original expression, take a limit, and I'm going to end up with 1 over f prime of x0. Okay, so with that, I can now use a definition of a limit to express the same statement in the following way. For any epsilon greater than 0, there is a delta greater than 0, such that x minus x0 being less than delta. This implies that this lengthy expression x minus x0 over f of x minus f of x0 minus a limit that this is less than epsilon, right? So this is just by using epsilon delta definition of the limit. Okay, so we have this. Now, further, let's recall one thing. We said, we proved before actually, that if the function is continuous on some interval and is one-to-one on the same interval, then that means that the inverse function of that f exists, and not only it exists, but it's also continuous on the image of the original interval, right? So if I have a one-to-one function on the interval AB that is also continuous on AB, then the inverse is going to exist because the function is one-to-one and is going to be continuous on f of A, f of B. So further, f inverse of y is continuous on f of A, f of B, as we proved before, right? And so saying that the function is continuous, so if it is continuous everywhere on f of A, f of B, in particular, it should be continuous at the point y0. So f inverse is continuous at our selected y0, which is the same thing as saying that for every delta greater than 0, there exists another number, a gamma greater than 0, such that if I have y minus y0 less than gamma, this would imply that, now what does continuity means? It means that f inverse of y minus f inverse of y0, that this is going to be less than delta. Right, so here, because I already used epsilon in this statement, right? So now I'm using delta instead of epsilon. It would be the same delta as I came up with here. And then y minus y0 is less than gamma will ensure that f inverse of y minus f inverse of y0 is less than delta. All right, so now let's see, what do we have? So therefore, if y minus y0 is less than gamma, then f inverse of y so then f inverse of y minus f inverse of y0 is less than delta, and therefore, so now if I use, well, actually, let me write something else first, or f inverse of y minus, who is f inverse of y0? Right, f of x0 is y0, so f inverse of y0 must be x0. Right, so this is the same as that. So then if f inverse of y minus x0 is less than delta, then I can use f inverse of y instead of x in this statement, right? So if x minus x0 is less than delta, then this is true. But if I use f inverse of y instead of x, right, then again, f inverse of y minus x0 is less than delta. So therefore, we get that absolute value of f inverse of y minus x0 divided by f of f inverse of y minus f of x0, that this is less than epsilon. Right? Okay, so again, basically what I did, I simply replaced x by f inverse of y. All right, but then if this inequality is true, then we're going to conclude the following. Because f inverse of y is equal to x, right? And f of actually, no, let me write it differently. Because x0 is equal to f inverse of y0, and which is the same statement, f of x0 is equal to y0, we conclude that the following is true. If y minus y0 is less than gamma, then this statement holds, right? Because I don't need now intermediate steps because they're all valid. So as long as y minus y0 is less than gamma, this is true. But here I'm going to replace now things by everything expressed in terms of y. So x0 is f inverse of y0, so this becomes f inverse of y0. F of x0 becomes y0, and then f of f inverse of y by cancellation of f and n inverse will become just y. So if this, then absolute value of f inverse of y minus f inverse of y 0 is going to be divided by y minus y0, and this whole thing is less than epsilon. And this actually is now fitting the definition of a limit of f inverse at y0, right? No, not of f inverse, but a limit of some function at y0. As long as y minus y0 is less than gamma, this is less than epsilon, right? For any epsilon. And so therefore this is equivalent to saying that the limit as y goes to y0, and I'm actually missing here in all of these expressions an important component, right? Because my original limit was this, and I forgot to write 1 over f prime of x0, so minus 1 over f prime of x0 minus 1 over f prime of x0, and so the conclusion now is that the limit of f inverse of y minus f inverse of y0 over y minus y0, that this is 1 over f prime of x0. But then, of course, this limit is nothing but the definition of the derivative of f inverse. So f inverse prime evaluated where the limit is taken as y goes to y0, so this is y0. And so we're done. Okay, and so now we can use this type of a formula to figure out derivatives of a bunch of functions. So for instance, if, and that's how we have done it before. So for instance, I want to find the derivative of natural log of x. So what is f prime of x for ln of x? So how do we argue here? Well, we know that ln of x ln of x is the inverse function for e to the power x on the interval 0 to infinity, right? Certainly e to the x is 1 to 1 and continuous on 0 infinity, right? So e to the x, and let me denote it by something, f of x equal to e to the x is continuous, is 1 to 1 and continuous. On 0 infinity, and it's differentiable everywhere on the interval from 0 to infinity. So, and for example, given an x0 on the interval from 0 to infinity, and I'm not sure why I'm writing from 0 to infinity, because, let's see, so no, that's true, but this one is from minus infinity to infinity because exponential function is continuous and differentiable everywhere. So given any x0 on the interval from minus infinity to infinity, f of x equal to e to the x is differentiable at x0. And so it must be then that the log of x should be differentiable at the corresponding y0, right? So therefore, if I have x0 in the interval from minus infinity to infinity, then y0 equal to e to the x0 is going to be now between 0 and infinity. And by our theorem, well, actually one more thing. And f prime of x0 is equal to e to the x0, right? Because the derivative of the exponential is also an exponential. So from a theorem that we just proved, we know that f inverse is differentiable. So f inverse in this case is natural log of x, is differentiable at y0, and f inverse prime of y0 is the same thing as 1 over f prime of f inverse of y0. So f inverse prime, of course, in this case is log of x prime evaluated at x0, right? So I'm going to write it like this, that this is equal to that. Okay, and then what is f prime? F prime is e to the x0, so this is 1 over e to the x0. And who is x0? x0 is natural log of y0, right? Because if y0 is equal to e to the power x0, then x0 is log of y0. So what you get is 1 over e to the log of y0. And of course, e and log will cancel each other out, and so the answer is 1 over y0. One thing that I, again, should be careful about here, because log goes from y-axis to x-axis, I have to write log of y prime evaluated at y0. And so then if derivative of log of y is 1 over y0, then if I again interchange y and x, so interchanging y and x, we then have that log x prime is equal to 1 over x for all x greater than 0. Okay, and so that's how you compute the derivative of the inverse, right? It's always based on the derivative of that regional function, and then combining expression for the derivative with the relationship between the function and its inverse, you arrive at the final formula.